Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, let us try to cover as many interview questions as possible which are asked on Verilog. So without any delay, let's start with this particular session. And if you are watching this channel for the very first time and if you haven't subscribed, please do subscribe and like. So let's start with this particular video, and the very first question is design a 4x1 multiplexer, and it should be parameterized. Whatever the inputs which we are going to give is should be parameterized. We need to basically we need to design a multiplexer with configurable data width. So let's say this is my multiplexer which is given, which is a 4x1 multiplexer. 4x1 multiplexer, inputs are 4 only, you cannot change this, and select lines are 2 only, you cannot change this, and output is same. But the question is, whatever the I0, I1, I2 and I3 and Y, whatever you are going to give, this I0 width, I1 width, I2 width, I3 and Y width can be changed. It can be 8-bit, or it can be 16, or it can be 32, or it can be 64, and also the Y also, because if the input is changing, obviously it should also change, right? 8, 16, 32, 64, right? So this should be configurable. So this is what the question is. So what you can do is you can take your time, write down the Verilog code for this and try to get the answer done, and you can cross verify with my particular solution, right? And provided you should not get any latch conditions over here, you should not form any latch conditions over here, and whatever the code you are going to write down should be synthesizable. So these are the requirements which we are going to have. So yeah, you can start writing down. You can pause this video and you can start writing down. Yes, hope you have written the code for this. So let's see how to write down the code for this particular multiplexer, and also we will see how to develop the test bench for this, right? So let's say if I'm going to have input, let's say width -1 down to 0, I0, comma, input, let me copy this. I have 4 inputs. So basically these are all configurable widths. Width -1 down to 0, I1, I2 and I3. So like this I have. Now this width is configurable, right? So further I'm going to take a parameter width. Let's say as of now it is of 4 bits. Okay. And when the user wants to configure the width, he can configure it. And let me remove IT. Okay. So this is the inputs and the select lines. So input 1 down to 0, select. This you cannot configure it. You can have only 2 select lines. And here also I'm having 4 inputs only. Okay. But the width of the input is configurable. And output rich, it is width -1 down to 0, Y. So this is my outputs and inputs of this particular module. And let me write down an always block, always at the rate star, which is a combinational logic. Since mux is a combinational logic, I'm going to write it down. Now I'm going to use case statement for this. So what is the reason for case statement also we'll try to discuss over here. So case select, and let's say if it is 2 tick binary 0 0, then y is equal to I0, and 2 tick binary 0 1, y is equal to I1, and 2 tick binary 1 0, y is equal to I2, and 2 tick binary 1 1, y is equal to I3, and followed by default y is equal to 0, and end case and end module. So this is the code for a 4x1 parameterized multiplexer, right? So let us write down the test bench simply in the same module, in the same file, not in the module. So module mux underscore 4 underscore 1 underscore tb reg. So let me declare the parameter first. Parameter width is equal to 4. And let us, if we want, we can change it. So parameter width is equal to 4, and let me declare the inputs with reg. So width -1 down to 0, and here I0, and let me copy this, all this. Yeah. and let me change them. This is I1 and this is I2 and this is I3, right? Next I'm going to have the select lines, reg 1 down to 0, select, and reg width minus 1 down to 0 y. Okay, so these are the inputs and outputs. Next I'm going to instantiate them, so let me write down simply the design name. So mux underscore 4 underscore 1 is my design name, and followed by, let's say if I want to configure it into 16 bits, so here also I'm going to change to 16, and followed by dut, and let me instantiate them I0, I1, I2, I3, and select and y. Okay, so these are the instantiation I have done, and within an initial block, first let me initialize all the variables I0, I1, I2, I3, and select, which is equal to 0. Okay, and after some time, let me give all the combinations of uh, I0, I1, I2, I3, and select. So let's say select is equal to 2-tick binary 0, 0, and I0, let's say it is equal to 16 bits, right? So I can give like 7, and I1 is equal to 8, and I2 is equal to 9, and I10 is equal to 11. So at my output, I should get, sorry, I2 is equal to 11. Yeah. So 0, 1, 2, 3, I3 is equal to 11. So at my output, I should get y is equal to 7. So this is my requirement, and followed by end module. Now let me save this. Yes. So in the simulation source, I'm using Vivado. So in that, I need to make this as top, and let me click on run simulation. So there is some error it's showing. Let's see what is this error. I0, I1, I2, I3, and here also I0, I1, I2, I3, select and Y. We have done everything correct. And okay, let's check it out. What is the error it is showing? Okay, concurrent assignment to a non-net Y is not okay. So in the test bench, we need to write it down as wire. I've written it as reg. Let me write it down as wire, and let me run the simulation again. Yes, so we can see at the output we are going to get 7, and my select line is equal to 0. Okay, and it's configurable. So in the design we have given the parameter to be 4, but in the test bench we have configured it to be 16, right? Now let me synthesize this design, and let us see what kind of circuit or the logic diagram we are going to get, and let us use if else, and let us see what is that we are going to get, so that you can have a idea about what is happening when you are going to use case and when we are going to use if else. Yes, you can see we are going to get this kind of design where it's nothing but a simple multiplexer, right? Now let's say, suppose if I'm going to have, let's say if I'm going to use an if else block instead of this case statement, and let me write down using the if else. So if select line is equal to 2-tick binary 0, 0, then y will be equal to I0. Else if select line is equal to 2-tick binary 0, 1, then my y will be equal to I1. And else if select line is equal to 2-tick binary 1, 0, y will be equal to I2. And else if select line is equal to 2-tick binary 1, 1, then y will be equal to I3. Okay, so this is what we have written using the if else block, and yeah, so let us check it down what is happening if I'm going to use if else block. Simulation results will be the same. Let me run the simulation and let me show you what is the simulation results we are going to get. There will be no change in the simulation results. Let me click on run simulation and run behavioral simulation. Let's check it out. Yes, so there is no change in the simulation result. You are going to get your output as 7 only because you have selected the select line to be 0. Now let me close this simulation and open the elaborated design. Let's check the elaborated design. What is it we are going to get? Is it same or is it different? Let us check it out. So if I open this, I'm going to get, let me show it. Yes, so this is the logic which I'm going to get. It's not a simple parallel mux which I'm going to get. It's a kind of priority logic which I'm going to get if I'm going to use if else block. So that is a difference if you are going to use if else block and if you are going to use case statement. Okay, yes. Now, so that's about this particular question. So let's move forward to next question. We need to design a 4-bit priority encoder. So the second question which we are going to have is design a 4-bit priority. So coming to this 4-bit priority encoder, I'm going to have basically, uh, let's say it's a 4 cross 2 priority encoder. Then now, what is that I'm going to have is I'm going to have 4 input lines I0, I1, I2, and I3. Let's say if I3 has the highest priority and I0 has the least priority. Then if I want to, first of all, if you want to code for this particular priority encoder, obviously you need to know the table for this, the truth table for this, right? So without a truth table, you cannot code this. Now, so since I3 has the highest priority, if I3 is equal to 1, remaining bits, whatever it may be, your Y1 and Y0 will be equal to 1. If I3 is equal to 0 and I2 is equal to 1, whatever the remaining bits, your output will be equal to 1, 0. And if your I1 is equal to 1 and if your I0, whatever it may be, your output will be 0, 1 and followed by 0 0 0 1, your output will be equal to 0 0. So this is a table for your 4 cross 2 priority encoder, right? Now, so what is it we are going to do? So it's not 4-bit, it's 4 input priority encoder. Now, so if I want to code this and if I want to implement this, let us see how to implement it. So I'm going to create, first of all, let me comment the previous code which I've written, and let me declare one more module which is 4 cross 2 priority encoder. And let's say input I'm going to have as I0, I1, or I can use a vector. So I can simply write down input 3 down to 0 in and output 1 down to 0 out. Okay. So these are the inputs and outputs of this particular module which I'm going to declare. And next I'm going to use if else. So within an always block, it's a combinational logic. So always with rate start, begin if I of 3 is equal to 1. So generally I've seen so many people writing down like I is equal to, if I is equal to 4 tick binary 1 triple x. So generally what I see in people writing down the answers is if I is equal to 4 tick binary 1 triple x, then y is equal to 2 tick binary 1 1. No, this is not the case. Whenever the user is going to provide the input using the test bench, they are going to provide either 1 triple 0 or all any combination of triple x. So here you should not write down 1 triple x or some kind of thing because it is not going to match it. So you can simply write down I of 3 if it is equal to 1. So only if the MSB is equal to 1, irrespective of any other bits, if MSB is equal to 1, then your output will be equal to 1 1. Okay. And else if I of 2, if it is equal to 1 tick binary 1, then y will be equal to 2 tick binary 1 0. And else if I of 1, if it is equal to 1, then y will be equal to 2 tick binary 0 1. And the last scenario is y is equal to, okay, let us write down this one also. Else if I of 0 is equal to 1 tick binary 1, then my output will be equal to 2 tick binary 0, 0. Okay. So this is a condition which we can write down for the priority encoder and followed by n. Okay. So this is the logic. Let's write down the test bench quickly and let's check it out. What is that we are going to get? Let me close this and let me write down a simple model. Okay, what is the error it is showing over here? Okay, we should not start with a model with a number, right? So let's write down priority underscore encoder underscore 4 underscore 2. Okay, and here it is in. Let me declare it as in, and here it is out, or let me declare it as y only, and it should be rich because I'm using it in a always, right? So this is in and this is in. Okay. Yes, and semicolon. So priority encoder TB. Let me declare the inputs 3 down to 0 in and wire y. So let me first of all initialize them. Initial begin n is equal to 4 tick binary zeros, and after some time let's say n is equal to 4 tick binary 1100. So you can see I of 3 and third MSB and the next bit are equal to 1, but since n of 3 is equal to 1, you should get y is equal to 2 tick binary 1. If both are equal to 1, then since I of 3 has the highest priority, you are going to get your output as 1. Okay, so that is what we need to verify in our design. I mean in the verification, n is equal to 4 tick binary 1010. This also we will verify and followed by n. Okay, that's enough. These are the cases which I'm going to test it and followed by n model. Let's say if you want to change the priority, like let's say suppose if the LSB should have the highest priority, just write down this particular statement over here and write the statement over here. If MSB needs to have the least priority, that's it. This is what you can change it out there. So before that, let me save it and let me make it as top. Yeah, priority encoder is set to be top, and let me click on run simulation. So you can see y is showing to be unconnected and you haven't instantiated, right? So we haven't instantiated our design over here. So let me first of all quickly instantiate it. So you can, if you see anything like high impedance or some kind of thing, that means there is something missing or something uh, not connected or instantiated. That is the message you can find it out, right? So let me write it down after this declarations. So it is in comma y. That's it. And let me save this and relaunch it again. Yes, I can see in is equal to initially c and y is equal to 1. Okay, let me declare y to be of 2 bits so that I can see it. So y should be equal to 1 1 in both the cases. That is what we need to have it. Let me relaunch it again. Yes, so in both the cases y is equal to 1. Okay, yes. So this is how we are going to write down a Verilog code for a priority input, right? Now let's say suppose, now let's move towards the next question. So the next question which we are having is we need to design a parameterized D flip-flop or configurable D flip-flop with asynchronous reset, right? So that is what we need to design, and the reset is a edge triggered reset. That is what we need to have. So let's say suppose this is my D flip-flop which I'm going to have, and whatever the input which we are going to give it over here, this is configurable. Like it can be 1 bit or it can be 2 bit or it can be 4 bit or it can be of any bit. So that depending upon the input, you're going to change your width of your output also. So your output is also configurable. It can be of 1 bit, 2 bit, 4 bit, or so on. It can be of any bit. And it's a D flip flop, so you're going to have a clock. and you're going to have one more extra signal like asynchronous reset, or else you can also think of having a clear signal. Okay, so this is a clear signal which you are going to have. This should be asynchronous. Okay, that means asynchronous in the sense it is not dependent upon the clock. Okay, and this is only one bit. Okay, now let's try to design this D flip flop which is configurable, having an asynchronous clear signal and all. Let me come in this code. So let me write down simple module dff underscore configurable and the input, and it's a parameterized module if I want to configure. So parameter with, which is equal to, let's say it is of 4 bits, and input clock reset and output reg q and q bar. Now, so input we also have width -1 down to 0 d. Okay, this is my input which I'm going to give, and output which I'm going to have is q and q bar. Okay, these are the inputs and outputs which I'm going to give. And next what we are going to, let me write down in module. Yeah, now since it's a flip-flop, so I'm going to use a sequential block. It's a sequential block, so always at passage of clock begin, and it's a synchronous reset, right? So I'm going to have or pause edge of reset. As I've told you, if there is any edge of the reset, that is pause edge of reset, this block reset should be applied, right? So, and it's an asynchronous reset, so that's the reason I'm adding it in the argument. Now, if reset begin q will be equal to 0, I should use non-blocking, and here I can basically use a configurable thing which is width concatenation operator 0, because q might be of any bits width, right? So that's the reason I'm using this width as the replication operator. I'm using replication operator where width is nothing but actual width, and it is going to, for example, if width is equal to 4, then I'm going to assign 4 zeros to q. Okay, and width can change. Width can be 8 or width can be 16 or 64 bits. Accordingly, this number of zeros will be assigned to your q. Okay, and let me also make q bar is equal to 1. And here these are basically of type reg, so I'm using over here, and followed by end. And else if, so else what I'm going to do is q is equal to d and q bar is equal to not of d. That's it. So this is how I'm going to design it. Concatenation with an unsized literal will be treated as 32 bits. So you should not use 0 over here. We are going to write down one tick binary 0, and here also one tick binary 1. Okay, so if you are simply writing it as 0, it will be considered as a 32-bit zeros, and if you are writing it down as simply 1, it will be considered as 32-bit 31-bit 0 followed by 1 bit 1. So yeah, and this is the code which we have written for this. Now let's write down the test bench and let's check it out. What is it working? So let me write down module tb underscore dff, and I'm going to have the parameter declared. Let's say width is equal to 8. I want to have the width of this flip-flop to be 8 bits width, and dff is my design name underscore config, dff underscore c config, and dut clock reset, and what else I have, d and q and q bar. Let me also declare them. Reg width -1 down to 0, d, and wire width -1 down to 0 q and q bar, and also let me declare clock and reset. So these are all the inputs which we have declared over here, and I have instantiated these things, clock, reset, yeah. And let's also change the parameter value. So it's 4, right? So we are changing it to 8. Okay. And yeah, let me initialize everything. Initial begin, clock and reset will, and D will be equal to 0. And let me generate the clock. So within an always block, hash, let's take the clock to be 20 time units time period. And within an initial block, what I'm going to do is I'm going to provide them. So let's say, first of all, let me reset design. Reset is equal to 1. After 20 time units, let me remove the reset. And after some 20 time units, let me apply D is equal to 1. Okay, here D is of 8 bits width, right? So I can give any value, 8-bit binary 1011 underscore 0111 0110, right? So this is a value which I have given over here. Okay, 0311. And after some time at the next edge of the clock, I'm going to give another value. This is a value which I have given, right? Yes. And followed by end and end model. So let's check it out. What is that we are going to get? First of all, let me save this. And since I have changed the model names, yeah, let me run the simulation. Okay, I think we haven't connected Q and Q bar. Let's check it out in the design. Sorry, in the test bench. Clock reset D, Q and Q bar. Clock reset D, Q and Q bar. Clock reset D, Q and Q bar. Okay, we have connected them and we have declared them as wire itself. We haven't declared them to be of configurable width. That's the reason it's not getting connected to the other values. Output reg width -1 down to 0. So it's a single bit, right? We have declared it as a single bit. So only few bits are getting connected and another bits are left unconnected. You can see over here. Only the last bit is connected and remaining bits are left unconnected since we haven't declared with configurable width. Now let me run the simulation again. So let us check it out. What is that we are going to get? So if your D is equal to 0, your Q is equal to 0. And D is equal to B7. What about the Q value? Q is equal to B7. And let's say suppose, yeah, this is a value which we have given, and after B7 we haven't given anything. That's it. So this is what we are going to have, right? So this is how we are going to write down the Verilog code for a simple configurable D flip-flop. Okay, and this value we are not getting a D is equal to, okay, this is the same value, right? Yeah. Okay, so this is how we are going to write down a simple code for a configurable D flip-flop. Now, so that's about this particular video where we have tried to discuss few easy interview questions. These are actually very easier designs if you are already working with Verilog. But if you are a beginner, I hope this is very informative for you. And if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI, where we will try to discuss more kind of different variety of questions, right? Yes. So that's about this video. Thank you.